Here we have example 4, and again we're going to do the same thing. We've been talking about sets and what does it mean to be equal sets. So let's see how much you've learned. We have these sets here from A, B, C, D, E, F, G, H, I, and L. And they're all either described using set builder notation or the roster method. So our question here is, which of the following represent equal sets? So now I will tell you that there are 3 of them are equal sets, the others are not. So that may help you a little bit. I also want to remind you that this N means the natural numbers. So those are the counting numbers, 1, 2, 3, 4, 5, on and on and on. W represents the whole numbers, and the whole numbers start at 0 and then go 1, 2, 3, 4, 5, on and on and on. So just to remind you about those notations there. So why don't you go ahead and see if you can figure out which of these are equal sets, and then come back and we'll see if you're right. So go ahead and press pause now. Okay, so hopefully you did that and you looked at each of these sets and you said, okay, well, what do we recognize first? Let's take the set A, B, C, D. So are there any other sets that have A, B, C, D in them? And we see C does. So therefore A is equal to C. Not only do they have the same number of elements, they have the exact same elements. They're just in a different order. All right, well, what about this set B here, X, Y, Z, W? Do any of the other sets have X, Y, Z, W? No, they don't. So this one does not have an equal set. Now this would be equivalent to A and C, but not equal to. So you have to be very careful about that. All right, let's see, let's look at D now. D is the set of all x's such that 1 is less than or equal to x is less than or equal to 4, and x is an element of n. So if we were to write out that set using the roster method, that would be the set 1, 2, 3, and 4. So we don't have any other sets that are 1, 2, 3, and 4. So there's nothing. Again, it would be equivalent to C, B, and A, but it's not equal to, and that was our question. Okay, what about set E? Now set E is the empty set. So let's see, do we have anything else that is the empty set? Well, you might be tempted to say F is, but that is not correct notation. This says the set that has as its element the empty set, and that doesn't make sense. The set of the empty set. That's just, we don't talk about it that way. So this is not the empty set notation. G is the set that has 0 in it, but it does have an element. It has an element of 0, so that is not the empty set either. Here H, that is another way of writing the empty set. So we would say E is equivalent to H. Those are the exact same thing, just 2 different ways of writing it. All right, now finally we have this really weird set here, I, which is the set of all x's such that x is equal to 2n plus 1, and n is an element of the whole numbers. All right, so let's kind of write out a few of those so we see what we're talking about here. All right, so if I were to use a whole number which starts at 0, if I were to put a 0 in here, 2 times 0 would be 0 plus 1 would be 1. If I were to put a 1 in for n, which would be the next whole number, 2 times 1 would be 2, plus 1 would be 3. If I were to put a 2 in for n, then that would be 2 times 2, which would be 4, plus 1 is 5, and we would go on and on and on and on. So that's what that set looks like. Well, what about this set? Let's write some numbers out and see what it is we're actually working with. So this is the set of all x's such that x equals 2n minus 1, and n is an element of the natural numbers. So the natural numbers, remember, start with 1 and go 2, 3, 4, 5, so on and so forth. So if I start with 1, 2 times 1 is 2, minus 1 is 1. And then if I use 2, 2 times 2 is 4, minus 1 is 3. And then if I use 3, 2 times 3 is 6, minus 1 is 5, and so on and so forth. So by doing that, we can see that those sets are actually identical. So I is equal to L. They are the exact same sets.